Hi everyone, this lesson is for Algebra 2 Honors students. This is Chapter 4, Lesson 4.10 for Systems of Linear Inequalities. This is a precursor to basically solving equations or modeling problems with linear equations that have to do with, reality and word problems. So we are going to be working towards that actually on our very next lesson. Also today is super cool because we're going to be talking about our project and also piecewise functions. So and how that relates to our project. And one of the things that I really enjoy is always, when I'm creating these slides for you, is like finding the fun in math. Like, why not? Who knows what lurks, behind these super cool values here for my lines. And I guess that's not going to show up. Oh, there we go. And yeah, so you never know what's going to show up, right? Okay. Let's get started. First thing we're going to do is we're going to talk about our learning targets, basically graphing systems of linear inequalities, piecewise functions, as well as discuss our project. So graphing inequalities, we're going to start with these two equations and just graphing them. So graphing these, I'm going to solve for y, although I do want to very much stress that, especially with the traces and all of the things that we've been doing with matrices, yes, definitely, if you feel completely comfortable graphing by intercepts, do it. So this one, I'm going to solve for y on the first equation. So I'm going to get 4y is greater than negative 3x minus 12. I'm going to divide by 4. I get y is greater than negative 3/4 x, and then dividing by 4, I get minus 3. So here's one equation. I'm just going to box that up so I can easily get to it if I need to. The next question is, for this, is that the second one is going to be negative 4y greater than or equal to negative x, and then minus 8. So I'm going to divide by negative 4. I'm showing this one step. I know I didn't show it in the other problem, but only because when I do divide by a negative number, it does change the inequality, direction. Remember, this negative sign here is actually saying the opposite of greater than, which is leads itself to negative or less than. So then less than 1/4 x and then plus 2. So I'm going to box that equation up for that. I'm going to make this a little bigger and try to graph these. Remember, if you were just graphing one of these problems, like this first one, this goes negative 1, negative 2, negative 3, starting here, slope down 3 over 2, 3, 4. If I was just graphing this one right here, this greater than is just a dotted line, remember. Also note that if it's greater than that, what it's really telling me is that any value above this line, greater than, not including that line, but above the line, would be a solution to my problem. So like I could choose 0, 0, right, which is right here. That would be a solution. And so sometimes they're just going to ask you, for a solution, and sometimes they're going to, this definitely has two answers. But okay, so for the second problem, that's saying start at 2, so 1, 2, and then go up 1, and then over 2, 3, 4. So that's sort of a long slope, and that's a solid line. And that solid line, by the way, is saying, well, that's saying y is less than this value, where the other one was saying greater than. This is saying less than, which is all this down here. Now, you're looking specifically at the places where it has double shading. And that would just be anything in this area in here would be an accurate representation of the graph. So you would like double shade it. You can use colors, or you can use, whatever it is that you're using to double shade. And that's fine. Okay. All right. Next problem. Graphing these three inequalities. We have the first one, which is 2y is less than or equal to negative 3x plus 12. I'm going to divide everything by 2, and I get y is less than or equal to negative 3/2 x plus 6. So there's one equation. This one right here, I'm going to put up here. And so that's going to be 5y is greater than 2x minus 10 we get y is greater than 2/5 x minus 2. So here's my second equation. And then for my third equation, this one, I have negative y is greater than or equal to negative x minus 1, or y is less than or equal to, meaning change the sign opposite, of positive x plus 1. So there's that equation. So I've got three equations that I need to graph. And in doing that, so let's do that. So we have, the first one is going to start at negative 2, 1, 2, and the slope is 2/5. So up to 1, 2, 3, 4, 5. And so this is a dotted line like this because it's greater than but not equal to. And so shading wise, it's anything that's above this line right here that's greater than, up on top. The next one is, we just graphed this one, check. The next one is this one, and this one is saying, I guess I'll use the same color. Start at 6, so 1, 2, 3, 4, 5, 6. Start at 6. And the slope is negative 3, so 1, 2, 3 over 2. And so this graph is solid because of the less than or equal to, so solid line. And this one is saying less than, so you've got to, so on a line like this, it's a little bit tricky because less than is below. You always have to think, you know, if you have a line, where's below and above? So that is a little bit tricky, I get, but you know, that's this area here. So that's less than. So far, this is the area that's double shaded. And the last equation is starting at 1 here, and it's saying slope is 1 over 1, so 1, 1, up 1. So this line is a solid line also, and looks like this. And this is less than as well. So realistically, anything below this line. So now what I'm really doing is I'm trying to find where is everything triple shaded. Not here, definitely not here. And so to me, so like you have to just find that area that where you're talking about that is shaded. So I'm going to use just a little crayon tool. So it's got to be, for this one, see this equation right here? It's got to be less than this black line. So this is everything down here, right? But see this blue dotted line? That was up here. It had to be greater than that blue dotted line. So far, I'm just looking at this little space in here. And then the last area was, what was the other one? Here, starting at 6, and this had to be less than, so anything down here. And so probably what's going to happen is using this line here, this dotted line at some point is going to cross that line right there. And so what's going to happen is this will be everything in this shaded green region would satisfy my equation. So you do need to be careful in that if I ask you for a point of, give me a point that satisfies all three of those equations, right? That would be a point within this shaded region. And you would pick something that, is inside somewhere. You would pick a point and test it. You have to test it to make sure it's true for all three problems. So we're going to start with piecewise functions because graphing inequalities is, you've done that before. Piecewise functions, I love this picture because it's sort of like taking pieces of, if you've seen this film, and I'm a film buff, but Face Off is like where this guy takes the face off of the other guy and basically uses it to impersonate him, and it's very, very interesting. Anyway, it reminds me of piecewise functions every time I think of it, so that's why I put that there. I thought it was appropriate. But realistically, piecewise functions aren't actually a movie, and of course they don't have John Travolta or Nicolas Cage in it, though I did meet Nicolas Cage at one point. But anyway, imagine we only want a piece of that function. So like you only want not an entire graph, but just a piece of it. So what you're looking at, right here is this equation, which is f of x equals x plus 1. And so you see this graph starts at 1, right? And so the slope is up, 1 over 1. And so this is the domain is from negative infinity to infinity, meaning this is going to go on forever, right? So realistically, that's that graph. But what if I don't want like that entire graph? I just want a portion of it. So what would happen then, right, is I would change my domain. I would have a restriction, or what we call a constraint. Some people call it a restriction and some people call it a constraint. So if my constraint says, hey, I only want you to go from 1, which, well, let's say it's there, 1, let's say that's 1, to infinity. So this is going to go on, but at 1, it's actually going to start. So my line that, whatever it looked like before, now looks like this because I have restrictions inside of it. So that is a piecewise function. It's a function that can be put into pieces. So we can create functions that behave differently depending on our input value and also dependent on our restrictions, right? So for example, this graph here, right? Let's say this goes this way. That graph here means that this is y equals 5, but they're saying your domain goes from negative infinity to 0, but not including 0. See the big open circle here? So you've got to understand that when they're talking about piecewise functions, it remains a function. It has to be a function, meaning it does have to pass the straight line test. It means that for every value of x, you have one value of y. So that's why that's open, and then this point here is closed. And that's y equals x squared. And with this right here, right restriction, what this one is saying is that the restriction would be anything greater than, so x would be greater than or equal to 1, 0, okay? And then, so you would say y equals x squared, and then your restriction would be this, x has to be greater than or equal to 0. Likewise, for this one, you would say y equals 5, but my restriction for that would be x has to be greater, or actually for this, x would be less than 0, but not equal to. Okay, so piecewise function is a function that is defined as a sequence of intervals, meaning it comes in pieces. In that, as long as it says it's a piecewise function, yes, you have, it does have to pass the straight line test, which then means that in the, the little fine details, this could be solid. That then would have to be an open circle. And look at this. This is saying x plus 5. So that means that, let's say we started at 5, and then our slope went up 1 over 1. See this right here? This was that was my x plus 5. So started at 5 and went up 1 over 1, up 1 over 1, up 1 over 1, right? But also down 1 to the left 1. But my restriction or constraint says x has to be less than negative 3, which is here. Which means, therefore, right? Oops, let me get rid of that. Which means, therefore, that anything beyond this value, which let's say is negative 3, it doesn't include that. So that would be, could be open. Now, where the second equation says, hey, I'm going to start at 2. I'm going to go down 1 over 3, down 1 over 3, etc. So if that was my equation, right, then this is saying x has to be greater than or equal to negative 3. So that, because it's equal to, it would be solid, and it would go to the right. Now, you are going to actually use Desmos for this, and this is part of like what your project's going to look like as well. So there is this very cool YouTube statement website, and that's a URL that will take you to basically show you how to input them into Desmos, because there is a trick to doing that, and I do want to make sure that you are putting that in correctly. So you can just type in how do I type in piecewise functions into Desmos, and then there's a video on how to do that as well. So this is something that I typed into Desmos just so that you could see what this might look like. And if you notice that you type in your equation, but then here you notice the solution sets, which is this thing. Those are your restrictions have to be in solution set. So that's just a fun fact for you moving forward. That's how you're going to be typing that into Desmos. So this one right here, again, functions that are defined as sequences of intervals. I want you just to look at this. There's 3 different graphs for this one. This normally, by the way, they will say f of x, which, yes, is the same thing as y, and f of x is equal to x plus 1. And I'm just going to graph that just to show you again. This is 2, so this is 1. So this is 1 up here. So what this is actually saying here is that we're going to start here at 1. My slope is up 1 over 1, so that's here. And so this line actually goes like this, right? Normally, this is what my line would look like. Well, what this is saying is that x is less than -1. So at -1, which is right here, at -1, it doesn't have a value because it says it's less than, okay? And so what that means is any value less than -1. So this, yes, can keep going. However, anything to the right of that does not exist. So that's just gone. Likewise, for y equals x squared, normally you would draw a graph, right? And then you would put the values in like this, right? But because they gave me restrictions, and my restrictions say -1 to 1. So that means any value from -1 here to 1 here would be okay. And they're saying that it's less than or equal to, so yes, solid, and yes, solid. And then the last one is just y equals 1, which is, is just a line that goes straight across like that. But remember, if it has to be a function, then all of these values here are already taken. And it would make sense then to actually start my equation right here, which says x is greater than 1. And the reason why they said it can't equal 1 is because for this problem, you've already said it equals 1. So there's already a solid value there. So we're going to do one of these on our own, and I would urge you to pause the video and take a minute and graph this on your own, and then let's check it. Let's see how you did, okay? So pause it, wait. Okay, so I'm going to assume that you are now back, and we're going to graph all 3 of these. So this is saying y equals 3. So the first equation says y equals 3, or f of x equals 3, which is just a 1, 2, 3, a line at 3 that looks like this. Okay? Now, the only difference is that my constraint or / restriction says that x has to be less than 0. Less than 0. X has to be less than 0. So that means at 0 here, I do not have a value. It is less than that. So that means that there is no value at 0 or no value greater than for this equation because of my constraint. So that's open. So there's no value at 0. And all of these constraints, all of them, are on my domain. Okay? None of them are on my range. So, okay, so the next question says, hey, we've got f of x equals y equals -x. So that means that my slope is plus 0, right? So I'm going to put 0 here. And then graphing is slope is down 1 over 1, down 1 over 1, or up 1 to the left 1, right? So generally, my line would look something like this, right? And it would just keep going. Now, the trick with this is that this, 0, x is greater than or equal to 0. So, hey, that works right there at 0. And however, it has to be less than or equal to 3. So 1, 2, 3. So here's 3. So it could equal 3, which is down here at -3. It could equal 3, but that's it. It just goes from here to here, which means that the rest of the line, the entire rest of the line, is actually gone because I have a restriction that says I can only go from 0 to 3. And so that's it. Just this little area right here. And by the way, these are both filled in. Now the last one is saying y is equal to -3. So again, this is a line that goes through -3 like this. Now keep in mind, this has to be a function. If it's a piecewise function, yes, it has to pass straight line test. We already have a value here, right there. So therefore, it would be, make sense that it says x has to be greater than 3. Meaning this line right here wouldn't have a value at 3. So I'm going to erase the little red mark there and put that green mark back, because for my green line, right, this one here, I actually have values there. But anything above that, I don't. And so what that means then is anything over here to the left would not be part of my graph, okay? So this would be my piecewise function, okay? And I have everything past the straight line test. We're good. Okay, let's try this one. Again, I would pause the video, graph your lines, and let's practice. Just check to see if you can do, if you can create the lines that fit the constraints and restrictions. So this one is saying y equals, so this is saying y equals negative 1/2 x plus 3. My second one is y equals x minus 3, and my last one is y equals negative 2. So the first one at 3, so we have 1, 2, 3 dot here. Down 1 over 2, down 1 over 2. So this one is saying that for my line, x has to be less than or equal to negative 2. I only went to the right, so actually I need to go up 1 to the left 2, up 1 to the left 2, just to get some point values. It says x has to be less than negative 2. So here's negative 2, but less than or equal. So that means this is solid here, and this is going to go that way, which means that anything to the right that I actually was drawing is gone. Now, the next value is y equals x minus 3. So at 1, 2, 3, here, slope 1 over 1, so up 1 over 1. Just going to draw my line that looks like this. And then this one is saying that the values for x are greater than negative 2. So that means here, no value at negative 2. And then at 1, also no value. And so I would then lose everything that was outside of those constraints, or, outside of my little restriction. So those values here. And if I want to know exactly what this point is, and yes, you would need to know that, you would plug in, like, what's happening at 1. 1 minus 3. 1 minus 3 is negative 2. So at 1, negative 2, this value right here, there's no point. There's no value there. Likewise, at negative 2 minus 3, right? That's at negative 5. So, yeah, I don't have a value there. But you do need to know, like, what the actual values are, because they may ask you, hey, what's f, okay, like this. What's f of negative 2? I'm going to ask you that. And if I say, well, here's negative 2, which equation am I using? Do I use this equation right here, or do I use this equation here? Well, obviously, I'm going to use this equation up on top and not this bottom one, because at negative 2, I don't have a value. So at negative 2, I would go back up to this equation here, and I'd say, well, what is it? Y equals negative 1/2 x plus 3. So at negative 2, what's happening is, let's see, 2's are going to cancel, negatives are going to cancel, that's plus, so that's x, sorry, that's not x. So that's just going to be 1 plus 3, which is at 4. So at negative 2, this value at negative 2 is 4. So you just need to know that you can plug those values in, but it's very, very important that you know which equation to plug in. And then the last part of this problem is y equals negative 2, which is a graph, of course, that is this way, right? Y equals negative 2 is a line that does this. However, more restrictions, and that is x has to be greater than 1. So again, at 1, which is right here, right, I have no value here. And it just goes greater than 1, so any value to the right would be accurate, meaning nothing to the left is part of my graph. And let's see if I can get, let me just put a big open circle there. Okay, so that's my graph of my piecewise function. This one, I really like this example. Again, I would urge you to pause your video, but what I like about this problem here is that it has 3 different types of equations, right? You've got this graph here, which is a parabola. You've got this graph here, which is an absolute value, and you have this graph here, which is one of these things. It's a root. So, so pause, try to do this on your own, and then come back to it. So I'm assuming you did that. Where does this start on my x-intercept? X equals 1. So that would start here. At 1, here's 1. So for this one right here, that is this graph here. and it's x has to be greater than 1. So that means at 1, even though it starts at 1, at 1 I don't have a value. And so this is going that way. For this one, which is my absolute value, this normally would go here at 0, 0, and it would go like this. Get bit by a bee here. And it would go, it's back there. And so this is saying I only have values that work from -1 to 1. So what that's saying is all of this is really gone except for here. And so at 1 here, I actually have a value here and I have a value here. And that's like my absolute values. Just the arms got cut off there a little bit. Lastly, we have the parabola, and I would even possibly like plot some points because x has to be less than -1. So I would draw like -3, -2, not -1, but you know, because I know that that value doesn't work there. So plugging in -3, -3 times -3 is 9, -2, 9, -2 is 4. So at -2, 1, 2, I'm at 1, 2, 3, 4. So that value would work. Any value beyond that. So this value does work. I'm going to use a different color. This value does work. And at -3, 9, that works. Now remember what a parabola actually looks like. It looks like something like this, right? So if I had this graph and I put it here, right, that would look like that. It would just go up like that. But however, the parts that are from 0 to -1 doesn't exist. So this little part down here is actually gone. And so I'm going to try to make this like down here and then just lose that little part here. And so that when I put this in, it's looking something like that. Okay, so it doesn't, there's no value here. That's an open circle for the red, but a dark circle for the black line. That's the absolute value equation. And so there's my piecewise. All right, passes the straight line test. So you do have homework that is linear inequalities, but you also have a quiz review today. This is Wednesday, and which is, I think, what, 9:23? Yeah. And you do have a quiz on 9:30 that's covering all of these sections. The quiz review is in addition to this homework right here, which is only 4 inequality problems, so don't worry about that. What the exciting news is that we have a project, and I just want to talk about that just a little bit because it actually entails piecewise functions. In that, let's talk about that. So piecewise functions, obviously, this is a little bit more advanced than what I'm expecting from you. I am asking for a piecewise project, and I'm not necessarily asking for a function. Okay, so that means that you could be creative. You're going to use Desmos. You could use, you know, something. You could write your name. Obviously, that's not going to be a function, right? So I want you to have fun with this. I want you to be creative. I want you to create some sort of piecewise function that maybe depicts something that you like, that you're interested in. But I don't want you, it's not going to be that difficult because the rules are to create a piecewise picture. And I stress by saying picture, not function, because it can be a function for sure, but it doesn't have to be. You'll need only 5 steps. So like this graph right here has 1, 2, 3, 4 steps in it. Don't exceed 15 unless, you know, you really understand that you're putting in a lot of time. You need to use at least 3 different types of functions, meaning a quadratic, a linear, an absolute value, or like the last problem, we even had a square root, right? I want you to, when all is said and done, you're going to take a screenshot of your image that's on Desmos, and you are going to, and it also has to have the equations next to it. So be like picture and then equations. Be creative. It doesn't have to be a function, but be aware that, you know, I have been doing this for a while, and I do love Desmos, and I'm on that side all the time. Don't create something that is already done. And I know there is so many plethora of projects that are already done. Try to create something that's new. that's unique to you, that's going to be fun, because I really want you to have, for our first project, I want you to have fun. And like I said, 5 steps. So that could be a quadratic, could be a linear, could be a circle, could be, right? Because remember, it doesn't have to be a function, it's just a picture. And, you know, whatever you decide to create, I hope that it tells me a little bit about yourself. Okay? Have a great rest of the day. That's all I have for you. The project actually is due October 2nd. So put that on your calendar and make sure that you are leaving time for that. All right. Thanks for watching.